I'm pleased to welcome myself to give you a talk now. We've heard a lot of things. We've heard about clays. We've heard about finding those clays, calcining those clays, strength, durability, all of these things. So that was kind of the knowledge that we collected over time. You can understand the number of people who have worked behind this. Here at IIT Delhi, Professor Raman Ketu is from IIT Madras. At IIT Madras, there were a huge number of PhD students who had worked on this project. All of that put together gave us the confidence to develop a standard on Lc3 to tell people that now you have a standard. If you follow this, you would have a safe cement to use. Of course, our knowledge has developed further, and there are new things that we would like to add to those standards. But once we are confident about that, we propose that to the Bureau of Standards, and they take it through their process of modification. But let us look at the current status of the standard. Let us look at what's in there, why is it in there, how can it be developed further, and how do we integrate that into practice. So I'm going to try to merge together a presentation on what is there in the standards with how you can produce and use Lc3. That's what I'm going to talk about. I am talking about the Indian standard. We're going to talk about these subjects, but I'm not going to go through the list right now. This is the standard that was finally published by Bureau of Indian Standards in 2023. IS 18189, it's called Portland Calcined Clay Limestone Cement. The reason we have Portland first is because we expect that the largest component is going to be clinker, Portland clinker, then calcined clay, then limestone, and that's why they are in this order. But then now we realize it may not necessarily be the case. Well, it's a cement which is an intimately interground or a blended mixture of clinker, calcined clay, and limestone. We already know that. There are other standards that may not specifically say that this is the cement that you can make, but there are other standards that allow the production of Lc3 other than the Indian one. There is the European standard EN 197 Part 5, which is a non-harmonized standard, which is being accepted by several European countries now, is going into the concrete codes as well. There is the ASTM standard C595, which also allows a similar composition as the Lc3 code in India. And there is the Cuban standard. There's a long history with Cuba, because Cuba is essentially the place where Lc3 started. They also happen to be the first to have a standard on ternary cements, which includes Lc3. But India was one of the first places that had a standard specific to Lc3, which is both good and bad. It's good because we are recognizing the type of cement. It's bad because it ties us down to a specific composition. Well, that can be good as well in terms of production. The standard says that we would be using a clay with at least 40% of kaolinite content. And we have seen that in the presentations yesterday. With 40% kaolinite content, we are able to achieve similar strengths in the cement and the concrete as we achieve in the case of OPC. Of course, you can mix something with 5% kaolinite in it, but then you are not going to get the strength that you expect in a cement. You want your cements to at least perform as well as the current cements that are available in the market, if not improve the strength, right? Which is why this lower limit has been defined. And we say kaolinite because we've talked about it before. Because of the specific structure of kaolinite, the calcination of kaolinite is easier. Now we are finding that other clay minerals can also be calcined and can give you a good strength, but then we will have to go through a modification of the standards to be able to explain that. The standard says in the clause B.2.3, I'm going to jump around the clauses that are there in the IS code. So this is from the annex. It says that, all right, you want to look for a clay of 40% kaolinite content. One way of doing that is to look at the XRD value, but we realize you don't all have an XRD. The other way to look at that would be using a TGA, but we don't all have a TGA equipment available with us. So what you do is, you take the clay, heat it to 300 degrees centigrade, measure the weight, heat it to 750 degrees centigrade, measure the weight change. If that weight change is more than 5.6%, you are likely to have a good kaolinite content or 40% kaolinite content in the clay. And yesterday, Dr. Rakhi talked to you about this and explained where this number 5.6 came from. Now, one thing you have to realize is 300 to 750 is a wide range of temperatures. Starts from here, goes up to here. in most of these clays that you see over here in the thermogravimetric analysis, the decomposition actually happens in a narrower window. But in some clays it happens at a lower temperature, in some cases in a higher temperature. That's why we have to take a wider range of temperatures over there. However, there may be other minerals that may decompose. You may have goethite, you may have gibbsite that may decompose at lower temperatures and may give a contribution to the loss on ignition. The loss on ignition may even be higher than 14%, which is the theoretical maximum for 100% pure kaolinite. It does not mean that you have found a 500% kaolinite clay or 130% kaolinite purity clay. It means that there may be other clay minerals mixed with that. So this is not the final definitive test for the purity of the clay that is required, but this is a required test. If you don't get this, your clay is unlikely to be good. There are other tests as well, but one more important thing to keep in mind is if you have a clay with an even higher purity, it does not necessarily mean that the strength is going to be higher. You see here, going from a 56% kaolinite clay to an 80% kaolinite clay, you see that the strength is actually reduced, and this is what Professor Sri Krishnan talked about yesterday. That because higher purity clays can kill clinker hydration. So we have been recommending a range of 40 to 60% kaolinite, but that is a very general range. Your required range may actually be lower than that. So those are some things that you have to consider. When we talk about the composition of Lc3, in the Indian standard, we have a minimum clinker requirement of 50%, a maximum requirement of 80%. The clay content can go from 10 to 35%, the limestone from 5 to 20%. According to this code, if you could produce a cement that has 50% clinker, 25% calcined clay, and 20% limestone in this, not 30% calcined clay. So I recommend if you have a higher purity clay, which was going to give you a lower strength, reduce the amount of clay, dilute the clay. You would have to do those kind of optimizations for your particular compositions that you have, and then you would go to the production process depending on what you have. So a production process, okay, I had modified the slide a little bit, but that's all right. The production process would depend on the material that you have. The first thing that you would do is take the raw clay, make sure that it has the right loss on ignition, make sure you've tested it using XRD and TGA, the way we had talked about yesterday, or using some other tests that I'll again talk about right now. Crush the clay to the right size to achieve calcination. I'm going to talk to you about flash calcination and rotary calcination in a few slides, but depending on the process, you would have to crush your clay to different sizes. Normally what we say is that when we are calcining the clay in a rotary kiln, we try to keep a feed size of around 2 centimeter, 2.5 centimeter, 1 inch. So most of it passing through 1 inch. If you have to do a flash calcination, you keep a 2 millimeter size. We know that clay is a fine material. When you try to crush the clay to a finer size, a smaller size, you get a lot of dust. Handling that dust can be a problem. That is why it is not a very good idea, according to us, to crush it to a very fine size. You may end up getting a lot of dust. Your ESPs, your back filters may fail because of that dust. You may get a lot of pollution on the plant as well. So I would not recommend crushing it to a very fine size. The moisture content also plays a role. If your clay is very dry, that does reduce the calcination energy, but that also gives you a lot of dust. So you may have to optimize between the dust. You may have to design your back filters or your ESPs in such a way so that you're able to handle all of that dust and recirculate it back. The important thing is this dust, this finer part of the clay will be more pure, will contain more kaolinite. You cannot afford to lose it. You have to recirculate it back in the system. Make sure it's calcined and it goes back into your cement, because that is where your reactive part is. After you've done that, you calcine the clay. Once you have calcined the clay, you make sure your loss on ignition has reduced to 1%, 1.5%, something like that. Because as you've seen yesterday in Menaz's presentation, if you calcine the clay too much, if you go to a very low loss on ignition value, you end up losing reactivity because sintering and recrystallization of spinel starts at those temperature range. So you have to optimize it. We find that somewhere around 1.5% is the target loss on ignition. After you have calcined your clay, you have two options. Either you can grind your cement by intergrinding everything, your clinker, your limestone, your calcined clay, your gypsum, Everything goes into the mill, be it a vertical roller mill, be it a ball mill. It goes in. Make sure you have a closed circuit system so that you're feeding back the coarser particles. You will have trouble with grinding that way because the clinker may be harder than the clay. You have to take care of that. I'll talk about that in a little bit. There may be the option of separately blending the materials. Grind the calcined clay, limestone along with a little bit of gypsum together. You produce what we call Lc3. And Professor Ravindra Ketu came up with this term Lc3 one day. He said, then why not let's talk about Lc3 instead of these things. Instead of talking about Lc3. You make this Lc3, the advantage is also that you make a pozzolan, essentially, that can be used by the concrete industry. So you can use it in a ready-mix concrete plant, or in your site, at your site, you're more flexible with the amount of cement versus the clay that will go into your cement. So it gives you a bit of flexibility. And then you separately blend them together. There are some plants that blend together slag and clinker after grinding them separately, because slag has a lower grindability than clinker. You could do the same over here, but be careful. Clay particles stick to each other. You have to make sure that there is no sticking of the particles. So you have to have sufficient hot gases in the system to make sure that those particles are not sticking together, and you have a proper and intimate and uniform blending of these materials together. Well, the first step when you have to characterize the raw clays, you could always use the XRD and the TGA to do that, like I talked to you about that earlier. But remember that in the first step, when you're looking for the clays, you have to carry out prospecting. You have to go to areas where you have to look for areas where this clay is available. It may not be available close to your plant. You may not know where this clay is available. It's very important to understand what the economic effect of that is going to be, what the sustainability effect of that is going to be. Usually we are able to find the clays near the plants, but the data is not easily available because this is not the type of clay that people have been looking for. They have been looking for other types of clays which have more silica content, except if you're producing white cement, you may have been looking for kaolinitic type of clays. The most common tool that the cement industry uses to identify raw materials is XRF. XRF is quite widely available at cement plants now, and people like this technique because it carries out a lot of the measurements that you have to do otherwise. It carries that out relatively quickly. But XRF, I'm going to show you, is not a good way to identify the right type of clays. It could tell you how much alumina you have and how much silica you have, but that may not correlate very well with the loss on ignition value. You may have big errors in that measurement. That alumina that you measure over there may be present in other minerals. It may be present in other clay minerals like halite that may not be very reactive. It may be present in gibbsite that you may not be interested in muscovite that you may not be interested in. So it's important not just to carry out the XRF measurements, but also to use other measurements like XRD and TGA to identify whether or not you have those clay minerals. Dr. Raki talked about that yesterday. Even other people have even used alumina to silica ratio, but then that also gives you a high error. This is what the accurate calculation would be, and these points show you what you can measure using the XRF. The error is just too high. Prospecting is a difficult, time-consuming, and costly process. You do not want to use a low accuracy measurement in order to decide whether you want to buy a mine or not. So you have to be careful about that. If you don't have an XRD or XRF, you could go for live reactivity test, but we will talk about the methylene blue test afterwards as well. Like I said before, if you have a high grade clay, it will not just be expensive, it can also reduce the compressive strength of your concrete. It may also reduce the hydration. So you may want to dilute those clays before you start using them in your concrete. Not talking too much about it, but Srijit was talking about this article yesterday where you can find graphs that can help you decide how much of clay is to be put in your system, how much of limestone goes into your system, depending on what is the clinker composition. Now there's the next clause that is there in the standard, which talks about calcination, and it says that the clay shall be calcined by maintaining it at a higher temperature for a duration long enough to achieve temperatures above 750 degrees centigrade throughout the mass of the clay. The temperature of the clay shall be in no case higher than 950 degrees centigrade. We say that the solid temperature has to be above 750 degrees centigrade, which means the gas temperature has to be 850. That's when in XRD you see all of the, most of the crystalline material has been converted into an amorphous material. You see that hump over there. When you go to temperatures of 950 degrees centigrade or higher, you start to lose reactivity. You start to make spinel first, then you start to make mullite, cristobalite. You start to lose reactivity in the clay, which is why the standard gives you a certain calcination temperature. Right now, the standard only talks about thermal activation, but I'll talk about a couple of other ways to calcine your clay. Now, to achieve that 750 degrees centigrade, we are usually doing this in the lab using a muffle furnace, but you could do the same using other technologies. Using other technologies which are more common in the industry. We've talked about all of that earlier, but in the first production that we did in India, we tried to do a static calcination. We filled the clay into boxes, saggers, put them inside a big furnace and tried to calcine the clay. We never were able to reach the temperature that we wanted. Clay has a low thermal conductivity. Even when we had 1100 degrees centigrade outside, we had 450 degrees centigrade outside. We had a very non-uniform clay. On the surface, it was over-calcined. Inside, it was under-calcined. So we usually prefer more non-static methods for calcination. So you could have flash calcination. You could have rotary calcination. In flash calcination, you would calcine the clay within a short residence period of 3 to 6 seconds. To be able to achieve that, the temperature would be higher and the clay size would be finer. You would have particles of 2 millimeters in size. You pass them through the flash calciner, you would be able to achieve a calcination of the clay. Or you put it in a rotary kiln where you have longer residence period, usually of the order of 30 minutes, but you could have much longer rotary kilns as well that do drying. You remember the old wet process rotary kilns through which the material could pass in through hours. And we don't usually have those kilns anymore, but if we have them, we could still use them. The typical time is 30 minutes. You would use a feed size which would usually be below 100 millimeters is what I write, but we say somewhere around this size is the feed, and we try to avoid dust. In a smaller rotary kiln that had a residence time of less than 15 minutes, this was the feed size that we fed in, but you can still see the high amount of powder which causes problems of dust. So your system has to be able to handle all the dust. In a rotary kiln, typically the calcination temperature of the solid would be around 650 to 750 degrees centigrade. The gas temperature would be 850, 900 degrees centigrade at the most. But you would have to prepare the feed beforehand. You would have to crush it, homogenize it, feed it through the kiln. There will be some escaping material because of dust formation. There may be some segregation that will happen because of the rotation of the kiln, but we can live with that. There will be a small amount of lining that could happen depending on whether or not there's something melting in the raw feed. After that, you would take it to a grate cooler or something like that for the cooling. I'll talk about cooling a little bit later. You could do the calcination in a flash calciner as well. You have a more complicated setup. You end up having temperatures of around 1000 degrees centigrade. The size would be less than 2 millimeters usually, typically around 1 millimeter, but it could even be smaller. The residence time would be very short. But then the problem in these kind of systems could be that for certain types of clays, especially when you have iron and alkalinity in the clay, you could have lining of the flash calciner. You could have jamming of the fans. So the system could get blocked. There are more moving parts in here. We, from our side, from the Lc3 project side, have been recommending rotary kilns more than flash calciners because rotary kilns, the cement industry is more used to rotary kilns. It's a more robust system. The temperature can be easily managed. And the cost of these rotary kilns is going to be lower than the cost of the rotary kiln for clinker production because the temperatures are lower. The sizes will be lower, the residence time will be lower than what you require in the case of clinker. Dr. Neha will be talking about this later. But something that seems to be very important for the cement industry is the color. I don't really understand it, why we want to sell red bricks but not red cement. But if you use a reddish colored clay like the one you see over here, even after calcination it could stay reddish and it could give a red color, it could give a red paint or some sort of a color like that to the cement at the end. Holcim in Mexico decided that the cost for marketing a red cement was lower than the cost for controlling the color of the cement. they came out with a cement in the market which is known as a red hot and spicy cement, and that's what Holcim is selling in Mexico. But if you don't want to do that, you can still control the color of the clay. So even if you have a clay with 20% iron in it, very red clay, you could pass it through a reducing system in the cooler, which means in the cooler, you're firing a bit of fuel to achieve a carbon monoxide environment instead of an oxygen environment. Instead of getting hematite, you get magnetite. Hematite has a reddish color, magnetite has a gray color, and it maintains that color, and you also get some advantage in terms of water demand in your cement when you do that. The normal consistency also reduces. The amount of firing that you have to do is 1 to 5%. The fuel required is 1 to 5% of the fuel required in the calcination itself to maintain a CO environment instead of an oxygen environment. But I feel unnecessary cost. Spend that money in marketing a red cement, especially in your masonry applications. Red mortar should go very well with red bricks, I feel. So why not? But if you want to control your color, you can control your color. I want to show you a few examples. These are in no way marketing slides, but I want to show you a few examples of plants that have been set up or plants that are going to be set up by various companies or the inputs that we've received from various companies. This is a plant, this is a type of a flash calciner that was installed by FL Schmidt in France and Ghana. 525 TPD and 1200 tons per day production capacity with color control. You see here the same clay could be calcined to get a red color or a gray color in this plant. FLS also has a small pilot scale flash calciner in their lab in Denia, where they've been providing services to the cement company. This plant in France is already running. The one in Ghana should be running in a few months. This is CBI Ghana, a partly Heidelberg owned company over there. Then there's this plant in Ivory Coast. One day, a few years ago, I think around 2020 or so, we were suddenly surprised to know the news that Ivory Coast is already producing Lc3. This plant was supplied by APAC, which is a Spanish, Portuguese, Italian company. They have manufacturing facilities at different places. And they have supplied their kilns to several locations. Some of them are under supply right now, like the one in Oman that is listed over there. But Ivory Coast was the first one. Again, a rotary kiln. This is a double chamber kind of a rotary kiln. The first part does the drying. The second part does the calcination. If you remember yesterday in Menaz's and Raki's presentation, you saw that the first you have to dry the clay, remove the free water, and then dehydroxylate the clay. So they have separate chambers for the two processes over there. And these kind of kilns are also seen to be quite cost effective. The cost could be, for a full scale plant, could be less than $10 million. For an overall plant capacity of somewhere around 1 million tons per year. Dr. Neha is going to talk more about these things. Then this is another supplier, Low Shade, that is supplying both flash calciners and rotary calciners. They also have several projects which they have completed where they're producing, they have refurbished kilns in Brazil or in Colombia and Germany. They have a hybrid flash kind of a technology that is there. There are other suppliers as well. Sinoma, for example, has been supplying another hybrid technology that uses a fluidized bed reactor kind of a system. There are lots of different things that are there. There are new technologies that are coming up. There is mechanochemical activation that is coming up, where you can, instead of heating the material, you could take it to a high temp, you could mix it with some chemicals and grind it to a higher fineness to achieve the reactivity. There are electric calcination systems that are coming up that several companies are working on. There are solar systems that people are working on that will help us in further reducing the CO2 emissions and the cost of clay calcination as well. So after you've calcined the clay, there are many different options available. You'll see the economic part afterwards. After you have calcined the clay, you have to test the clay. You have to know whether the clay works or not. We talked about the loss on ignition test, but that is just a rough guideline. What we have found is that we have this line reactivity test in India, where what we do is we take the clay, calcined clay, we mix it with lime and water and sand. We measure the strength of the cube after 10 days. And if the strength meets the requirement of 8 megapascals, This is what we found from a large number of tests. If we had 40% kaolinite, we always got this strength of 8 megapascals if you're grinding the clay properly. So you grind the clay to 600 meters square per kilogram. After that, measure the strength in the line reactivity test. If you get the strength as 8 megapascal, your clay passes. The good thing about this test is that you can apply it not just to the calcined clay, but also to the mixture of calcined clay and limestone. Remember, I was talking about optimizing your Lc3. When you're optimizing your Lc3, you also have to decide the ratio of limestone and the calcined clay. So to decide that ratio, what you could do is you could mix your calcined clay and limestone in different ratios and carry out the line reactivity test. Even in those mixes, you're able to decide which of those mixes gives you a sufficient line reactivity value to be able to mix in your cement. So a simple test to decide the ratio of the different materials that are going into the concrete. One thing you have to be careful about, Menas talked about this earlier, if you have a very pure clay, you may not be able to measure the optimum calcination temperature because you don't have enough calcium hydroxide. But don't use these very pure clays anyways. If you use these pure clays, put them in lower amount, mix them with the limestone, and then do the line reactivity test. In that case, you would not only be able to see whether the clay passes the 8 MPa requirement, but you will also be able to find out the optimum calcination temperature, which may be different for different clays. If a clay has more iron, that calcination temperature may be lower. If a clay has more 2:1 clay minerals, that optimum calcination temperature may be higher. So you can use these tests to identify also those optimum calcination temperature. But don't worry, you don't have to do these line reactivity tests for regular quality control. You don't have to do it for your hourly sample. You don't have to do it for your sample every 4 hours or whatever you're collecting in the plant. You can do this very complicated methylene blue test. Each of these tests may cost you as much as 10 rupees to carry out, right? 10 rupees or less, 10 rupees? Yeah. So very low cost tests can be carried out in 15 minutes. You can do these for the verification for the quality control in your plant. And this is a very commonly carried out test in the cement plant. You don't really have to train your staff because they're carrying out this test for your limestone anyway. But do remember to combine it with the specific gravity test that I'll talk to you afterwards. You can use this test also to assess how much of kaolinite is there in your clay. So Dr. Rashmi talked about checking your clays, different kinds of tests where you're getting your hands dirty with the test. You can also carry out methylene blue test to get an initial assessment of how much kaolinite is there in the clay, depending on what are the other impurities. And definitely see the quality of calcination. As the quality of calcination improves, the methylene blue value reduces. But unfortunately, when you overcalcine, the methylene blue value does not shoot up again. So you have to use the other test, which is the specific gravity test, to know whether you're undercalcined or not. So you have to measure two things. You have to measure the density and the methylene blue value. As you improve the calcination, the methylene blue value reduces. But if along with the reduction in the methylene blue value, an increase in the density has also happened, this means that you have overcalcined the clay. So you can use this kind of a graph to know whether you have undercalcined or overcalcined your clay. Of course, you could always use the XRD results. But the problem is these XRD results will only give you overcalcination when the formation of mullite has already happened, whereas overcalcination has already occurred over here when spinel formation has happened, which can be captured using the methylene blue, using the density test. Now we come to the limestone. The limestone is an important part. It's 15 to 20% of the cement, right? The interesting thing that the Indian standard says is that you can even put pure dolomite into the system. You can mix dolomitic limestones, and although right now you have 75% carbonate content, we are hoping that in the future this would be reduced because we have data that shows that low-grade limestone can be used. You can see here two concretes produced using limestone, another one produced using dolomite instead of the limestone. You pretty much get the same strength. You get pretty much the same durability performance as well. So you have the possibility of using waste limestone that may be lying in your cement plants right now. This is a cement plant where you see a mountain of the virgin limestone and a mountain of the waste limestone, which is taller than the original mountain, because you can't use half of the limestone over there, or other kinds of wastes that could be used and ground into the cement. But we've talked about that before. You see here, because we are using that higher amount of limestone, there was a question earlier, the loss on ignition value that is allowed is 10%. Pure limestone has 44% loss on ignition. which means if you're putting 20% limestone into the cement, 8.8% LOI could come just from the limestone itself. That's why the allowed LOI value has been increased to 10%. Then when we talk about manufacture, the standard says that you have to intimately and uniformly either grind them together or blend them together. We have had experience in different types of grinding systems, like open circuit ball mills doesn't work because you have materials with different grindability. You end up getting a cement which is not properly ground. You have to have a closed circuit ball mill, so you can do it in a closed circuit ball mill or in a VRN. Recently, we got very good results with an HRP and ball mill combination. Seems to work very well. So if you have that kind of a system, it could be very good. But when you look at the physical requirements that are there in the standards, they're there because that is what we expect them to be. But you may not necessarily follow these numbers over there. You may be much higher than that. One important thing you would notice is a 43 megapascal strength at 28 days. This is something we insisted on because when we found that as long as you're using a good quality clay, as long as you're producing the cement well, with the 40% kaolinite clay, we always got, and the production process was good, we always got 43 megapascal strength. That also ensured that you're going to get good durability, also a better carbonation resistance. So that was very important. The blade value seems to be very high. A lot of people say, I'll have a lot of difficulty achieving this blade. Our energy consumption for grinding will increase, but no. The clay is a very fine material over there. Because it's a fine material, without increasing the energy required in the grinding, you automatically get a higher fineness. In fact, I challenge you to produce an Lc3 with 50% clinker and 30% calcined clay with a blade fineness of 400 meters square per kilogram. You will always get a value higher than 600. Even when you try to increase the throughput of your mill, you will still get a higher fineness. That's because this fineness is given not just by the higher fineness of the particles, but also because of the shape of the clay particles. They are layered materials. They are like filled inside your microstructure like this, blocking the passage of the air, and when they block the passage of the air can't pass through. So I have this joke, which is not really a joke, which is actually the reality. When they carry out the worst possible grinding and they say, this is the lowest possible we can grind, I tell them to put the sample in the Bain fineness equipment. When they start the test, I said, please go have a tea, talk to your friend, come back. The test will still be going on after that. That's how slow the air passes through these. It does not mean that the cement is very fine. It's just the shape of the particles is such, it's not letting the air to pass through it, which is why the blade value appears to be very high. So 400 is the requirement, but believe me, you will have no difficulty achieving that requirement. What is more important is that you're properly grinding the clinker. If you do not use a grinding aid, the balls in your ball mill may be coated by the clay. Any grinding media may be coated by the clay particles, preventing a proper crushing of the harder clinker particles that are there in your mill. And we all know that clinker is important. Let me go forward a couple of slides because I'm running out of time. We all know that clinker is important. The clinker has to hydrate to produce the calcium hydroxide, and only then it will be able to react with the calcined clay and the limestone to produce more CSH and to produce the carboaluminate phases. If the clinker is coarse, which is what happens if you don't grind it properly, you end up with a system which has a multimodal particle size distribution. This red one is the particle size distribution of an OPC produced in the same mill where Lc3 was produced in a plant, and you see there are coarser particles, and these coarser particles are always clinker particles. You sieve the cement that comes out at the end in a 45 micron sieve, and you see that you have coarse clinker particles present over there that you need to grind properly. Now, if you grind that clinker a bit more, just improve the fineness just a little bit, not too much. You see how much of an increase in hydration you get. You see how much of an increase in the strength you get. Optimal grinding is very important. If you see all the things are working and you are still not getting the strength of the concrete, One of the possible things that is going wrong, 50-50% chance. The other 50% is the next thing. 50-50% chance that the grinding is not proper. Look at the particle size distribution, or sieve your cement through a 45 micron sieve. My thumb rule is no more than 5% should be retained in your 5 to 7%. No more than 5 to 7% should be retained in your 45 micron sieve. It is retained. If it is retained in 45 micron sieve, you have too much of coarse clinker, because your clay and your limestone will be anyway very easily ground to a finer size. So be careful about that. The other thing you could go wrong with is the casting. We talked about it yesterday. Lc3 has a higher water demand. More importantly, clay particles agglomerate. They stick to each other. If you end up having places where the clay particles are all bunched up together, you would not be able to get the strength or the workability that you require. It is important to disperse the clay particles. Even if your concrete looks nice and it is flowing, the clay particles will still be sticking to each other. It's important to use the right chemicals. Here I'll show you an OPC mortar cube and an Lc3 mortar cube, and you see this has not been properly compacted. We made the same mix without a superplasticizer and with a superplasticizer. Everything else was the same. We had the same flow. We just added 0.1 or 0.2% of plasticizer in this. See the change in strength that happens because your clay particles are dispersed properly. You'll have less of these problems after you've done a intergrinding properly in the cement plant. But if you're doing interblending, it's very important to make sure of this. Even if the workability is there, the clay particles should not be sticking together. We need to achieve dispersion of the particles, which can be achieved using some sort of a grinding aid. Once again, I call it a grinding aid, but it is a dispersing agent. Once again, but this is very important to achieve. And coming back to the fineness, even though your cement may appear to be fine, it may still have a lot of coarse particles. Something that is easier to measure, maybe quick to measure, and gives you a better idea is the standard consistency. If you have a good particle size distribution of your cement, you also get a lower standard consistency. And you know, this is a very high-tech test. Again, very expensive. You can see all the very expensive equipment that is used to carry out this test. You can easily carry it out in any lab. You're already doing this. And of course, the very expensive operators. You've heard, well, they are express operators. So you can see Menas Express trying to very quickly carry out the MC test over there. Now we have a team of people. Carrying out this test is actually not that easy. You have to know how to play that music properly. It's like playing a drum. And we have some people who are quite experts in that, but all cement companies have these experts because you cannot find out the setting time without doing this test before that. So it's a very simple test. If you manage to minimize the normal consistency, you have achieved a good grinding of the cement. It's a good simple test for testing that. Even when you've done all of this, it's very important to optimize your gypsum. And Srijit said yesterday, calorimeter is your friend. Calorimeter is your friend in this case as well. I still do not believe there are so many cement plants, not just in India, but around the world who do not have a calorimeter. Well, I am not that surprised now because last week I visited a cement plant in Australia that had never heard about gypsum optimization. I'm sure anybody who has worked in a cement plant has heard about gypsum optimization, has carried out gypsum optimization. The way we carry out gypsum optimization here is that we make sure that the smoother, softer silicate peak occurs before the sharper aluminate peak. If the alumina is reacting before the silica, it can kill the silica hydration afterwards. Increase the amount of gypsum, your sharper peak will move towards the right, towards the right. And when it moves towards the right, it tells you that you have the right amount of gypsum. We have this ICAL 8000 calorimeter from Calmetrix in our lab, which works very well. I think you've seen it yesterday, you'll see it here today as well. You'll see it in the lab session today if you haven't seen it yesterday. So using that, you would be able to get a good gypsum content. There's a paper that was published by Paul Sandberg and me on how we can use calorimetry to optimize the gypsum, and not just to optimize the gypsum, but also to optimize the alkalis in your cement. It's very important to make sure you have the right alkalis. With the right alkali content, you can have a good early age strength without losing the long-term strength too much. Here, these are alkali sulfates that we have optimized. This optimization is very important, especially when you go to low clinker cements. You already have a low clinker content. If something kills the clinker hydration or prevents the clinker from hydrating, you have even less amount of clinker that is hydrating or participating in the microstructure development. You would like to have the right amount of alkali so that your clinker is properly hydrated. Now, I've talked about a lot of different things here. I've talked about standards, I've talked about production, all mixed in together because production always goes in parallel with the standards. I hope that the standards would be developed more in the future so that we don't necessarily have to use the same kind of cement in all kinds of environments. I don't think it makes sense, as you saw in Lukesh's presentation, I don't think it makes sense to use the same cement in an environment where there is chloride ingress versus an environment where you have carbonation problems. But one thing that I can very proudly say is that if you look at the number of publications in calcined clay cement on Scopus, you will find that there are a huge number of publications from India on this during the last 10, 13 years. Sorry, this graph is a little bit old, but even if you download this graph now, you'll see a similar picture. This is a cement that was not invented in India. We got the idea from Cuba and Switzerland, but most of the development on this cement has happened in India. It is the Indian environment that we have considered for the production, for the standards, and all those provisions that are there in the standards right now are there because of the data that has been obtained in India. And that was the data that Rupesh was also talking to you about. There are a lot of things to be done to make sure that we're producing the cement properly. We are there to help you. We are not making profits from this. It's like I said yesterday, it's more of a loss-making operation. But the idea is that whatever knowledge or information that we have gained, by making all of those mistakes during the last 10 to 12 years, we would like to transfer them to the industry through this TRC. And Dr. Neha Gupta is going to talk more about the TRC afterwards. But then I talked about standards. Right now, the standards are telling us how to produce the cement or what to do or what not to do while producing those cements. Unfortunately, most of the standards that we have right now, they are prescriptive standards. These standards tell you put this in these quantities and you'll be fine as long as you achieve the strength. But may not necessarily work if you move from one environment to the other. May not necessarily work if tomorrow you have a new idea and with that new idea you would like to produce a new type of cement. Even if that cement works very well, it would not fit into the prescription even if it meets the performance. So we have now Ms. Anvesha Satpathy, who is also a PhD student here, who is working on developing multi-blended cements that could be more suitable for the particular application that you have or the particular raw materials that you have. You may say today that I don't want to produce a calcined clay cement because I have a lot of fly ash available with me. How would you be able to use that fly ash along with calcined clay? The basic idea behind that is what Anvesha is going to talk to you about now. So that's all for my talk. If you have questions in that, let's take that while Anvesha sets up.